In engineering, you run into these classic problems all the time. Here's one. You've got to move a liquid, but you need to push it higher or farther than any single pump can handle. So what do you do when one pump just isn't cutting it? Well, in this explainer, we're going to break down the really elegant solution engineers use to literally double their power. This is the fundamental challenge, right? Your system needs more pressure, what we engineers call head, than one pump can possibly deliver. The solution, it turns out, is all about a clever way of combining forces.
All right, here's our game plan. We'll start by defining the high-pressure problem. Then we'll dive into series versus parallel connections. And after that, we'll decode the all-important pump curve to see how this all works visually. And we'll finish up with some absolutely critical safety checks before a quick summary. So let's get into it.
So first up, the high pressure problem. And look, this isn't some rare, super complex issue. It's a really common engineering challenge. The system you've designed just demands more oomph, more pressure than any single pump can provide.
And the solution? It's connecting pumps in series. The principle behind this is just beautifully simple. You're basically adding the pressure from each pump together to create this combined force that's way greater than what one pump could ever do on its own.
Now, to really understand why a series connection is the right tool for this job, we need to talk about a crucial distinction. See, there are two main ways to connect pumps, and they achieve completely different things.
In a series setup, think of it like a direct handoff. The outlet, or the discharge, of the first pump feeds directly into the inlet, or the suction, of the second pump. So the liquid gets a pressure boost from pump 1, and then, bam, it immediately gets another pressure boost from pump 2. This chart makes the difference crystal clear. A series connection, that's all about increasing pressure, or head, while the flow rate pretty much stays the same. A parallel connection does the exact opposite. It boosts your flow rate, but the pressure doesn't really change. It all boils down to a super simple rule. Series is for head, parallel is for flow. All right, to really truly get a feel for this performance boost, we need to look at the pump curve. This simple graph, this is the key. It's how we visualize exactly what's happening when we hook two pumps up in series. But first, let's just make sure we're all on the same page with the key term, head, which we represent with the letter H. In the world of pumps, head is just our way of talking about the pressure a pump can create. The easiest way to picture it is the vertical height it can push a column of fluid. That's it. Okay, so this graph here is our baseline. That solid blue curve shows what a single pump can do. The dashed line is what we call the system curve. It basically represents what our pipes and our system need. And where those two lines cross, that's the operating point. It's where a single pump would naturally settle in and run in this system.
So how do we figure out the new curve for two pumps? It's actually just simple vertical addition. You pick any flow rate you want, you find the head that one pump produces at that flow, and you just double it. You're adding the head from pump 1 and pump 2 together. You plot that new point, do that a couple more times, and you've drawn your new combined performance curve.
And here it is, the final result. That new orange curve, representing our two pumps, is shifted way up. Now look where it crosses our system's requirement curve. This new operating point is much, much higher, showing a massive increase in head with just a tiny little bump in flow rate. This is exactly what we were aiming for.
Okay, now that we've got the theory down, we absolutely have to talk about the practical side of things. Because in the real world, if you overlook a couple of key details, well, you can have catastrophic failure. These are things you can never, ever ignore.
So before you install anything, you have to verify two critical things. First, the pressure rating of your entire system. And second, the risk of something called cavitation in that first pump. Cavitation is just the formation of these really destructive little vapor bubbles. You check for it using a value called NPSH, which basically tells you if there's enough pressure at the inlet to stop the liquid from boiling inside the pump. This quote from the field is something every single engineer should have taped to their monitor. The final pressure coming out of that second pump is huge. It's the sum of both pumps. You have to be absolutely certain that every single component downstream, your flanges, your valves, and especially the pipes themselves, can handle that massive combined pressure. That first pump is the most vulnerable link in the whole chain. If it doesn't have enough pressure coming in and it starts to cavitate, it's just going to feed a stream of those destructive vapor bubbles right into the second pump. And that can destroy them both fast. So let's bring this all home and tie it all together with a quick summary of the key takeaways. This slide really sums it all up perfectly. The concept? Connect in series to get more pressure.
The calculation, just add the head values vertically on the performance curve. The operation, your new operating point moves way up. And most importantly, the safety checks, verify the pressure rating of the whole system and check the NPSH for that first pump. So, we've cracked the high pressure problem. But that brings up a really good question, doesn't it? What if your problem isn't pressure at all? What if what you really need is more flow? Well, that of course needs a completely different solution. And that's a fascinating story for another time.